Imagine you went and bought some groceries. You were walking down the alley, trying to find your favorite snacks and food that you are going to need next week. And like you got a frozen pizza, some ice cream, some vegetables, eggs, and yeah, some paper towel. Even got a bottle of orange juice, okay? Now the cashier put everything into one giant bag. You grabbed the bag, got back home, stared at bags of items, tried to put them into the place where you should go. But this is summer and your ice cream and frozen pizza were melting, so you need to put them into the fridge first. But the bag is small. You have to grab the item on the top first, then put it on the table, and then you can grab the second item underneath it. By the time you finally got the ice cream out, it already melted. Yikes, right? This kind of stuff happened all the time. And this got people start thinking that if there's a magic bag, that the cashier can put that item really quickly, while they can retrieve the ice cream or the frozen item first when they need to. But does that kind of bag exist? Well, the answer is no, because there's no magic in this world. But there is something that's quite similar. It's called the priority queue. This is a term in computer science. Sometimes you'll hear this in computer engineering courses as well. Priority queue means an abstract data type that works like a queue but have priority properties in it. When the computer program interacts with this queue, the next served item will always have the highest priority among others, or at least has the same priority with others. In real life, people just know which items has more priority, and they will do that first. But for a program, they do not know. Everything they see is just pure numbers, bunch of 1 and zeros. Even people will not know if there's anything important in those binary information. So, we have to come up with logic that could find which segment of data is more important, and the program will then do the operation based on that information. A queue has 3 important things. 1. To pop or to grab things from the front of the queue. 2. To push or to put things at the end of the queue. And 3. A place to store items that got pushed into the queue. In order to do this step as efficient as possible, we have to design a structure and operation that got optimized the most. To optimize the pop operation, we want the front of the priority queue to be as small as possible, so that we can just remove it from the queue and pop it out by only executing one operation. To optimize the push or insertion operation, we want to keep creating branch at the end of the queue, so that every time when we insert an item, we will only need to create a new item and put it at the end. If we put these 2 concepts into a picture, we can see what we want is something very narrowly at the front and very wide at the end. This is a tree. There are 2 kinds of tree. One, you must keep track your child, which we call explicit tree, and one we call implicit tree. Implicit tree is a type of tree that we do not store their children into a certain position in the memory location. Instead, we calculate them based on the position. The advantage for this tree is that we can implement it with a simple array with no additional structure. Now we have tree selected, and by following the definition, we should create a tree that the root has the highest priority conceptually, and each one of the children of it should have lower or equal priority than itself. But wait a minute, why is it optimized this way? What is the difference between this structure and other structures that could also reach the same functionality? Haha, great question. You see, there are many different types of data structure that we can use. They all can reach the same functionality to work as priority queue. But what we need is the fastest, the best, so that our ice cream will not melt during the hot summer. Let us look at a normal sorted array. We could use binary search in the array to find where to insert the new items with an O of log of n time complexity. But shifting everything behind it or in front of it will still need to have an O of n time complexity. How about a sorted linked list? For a sorted linked list, the insertion and deletion only need to replace two of the pointers, which is an constant time complexity. But the program have to go through every single node in the queue to find where to put it, which will give us a total of O of n time complexity. BST, or binary search tree, will use binary search and resulting in log of n complexity in finding position. And the insert or delete operation will also cause log of n complexity, which has a total of O of log of n time complexity in result. But when consider heap structure, which is the structure previously introduced, in the worst case, it will cost n log of n to delete and insert a node. But because the size grows in 2 to the n, there will be at least half of the nodes in the last layer of the structures and few layers higher. So it really costs, in average, and constant of time complexity. Wait. You said constant time complexity? What? Okay, let me explain. First, we will have a root. Then we have two of the children of the root. Then each child will have two more kids. So we will have 4 in the last layer now, and then there's going to be 8, 16, 32, 64, and so on. As we can see, for each new layer typically, we will have exactly 1/2 of the size of the whole queue. And a few layers above the last layer will include most of the nodes. So we only need 1, 2, or 3 constant time search instead of log of n search, resulting the constant time complexity in searching. That is the reason why the heap structure is so much better than those other structure. Wow, that's a lot of information to take in, isn't it? Let's go back to the ice cream case and make it more visualized and how this priority queue works. Okay, you got all the stuff you need and went to the cashier. You told the bag that you want to put the frozen thing on the top of the bag. And this magic bag, or heap priority queue, somehow nodded to you. The staff at the cashier will always put the item in the very end of the bag. This magic bag will check if this is ice cream or any of the frozen item which have prior priority than other stuff. If it is a frozen item, the bag will proceed to swap that item on the top of the other stuff. This is a function called insert key in priority queue. We add this item into the last position of the array, and then we start to check the priority of the new item is higher than its parent. If it does, then we swap them until it does not satisfy the situation anymore. Okay, now you got back to home, you open the bag and you can only see the very top item in the bag. This item is whether a frozen item or your favorite ice cream. The magic bag follow your order and give you the desired item on the top. This is also a very similar function when we create for the bag, like get max. To get the maximum or the highest priority of the tree, we can simply check the root of the tree. Since the top of the tree always have the highest priority than any other elements in the array, or at least equal to them. Now you grab the first item out of the bag, and the bag closed to reorganize the structure again. When the bag opened again, there is something that has second highest or equal priority on the top. To remove the highest priority tree node, the priority queue simply copies the value of the last item in the array, put it in the root, and delete the final node. Then we perform a check to see if this new value is less priority than any of its child. If it does, we swap them until this is not valid anymore. You see I use the term back, front a lot. This is because we usually create heap priority structure with an array, something like this, very trivial. Then let us highlight the first layer in the array. Because the root will have 2 children in the next layer, so it will mark the following 2 nodes in the array to represent the second layer of the tree. Now each the child will have 2 more children, so that makes the third layer to 4 nodes. Then 8 nodes in the fourth layer, fifth has the 16, and so on. Here we can kind of understand how the implicit tree looks like in an array. We can use some simple calculation to find out which index contain their parents and children, based on the model that we have here. To find the parents for the current node, we can take the current index of the nodes minus 1, then divide the outcome by 2. Since it's an integer division, all remaining will be discarded. So how about the child's index? Well, we just need to reverse the previous process and that's it. Therefore, for the left child, we can use the current index times 2 and then add 1. For the right child, it's just the left child add 1 once more time, because it's on the right. Easy, right? And the program loved to do this kind of simple math. Quick math is much faster than the if statement in general. But can this structure only work with a sorted or empty array? The answer is no. This structure can use to sort the unsorted array and convert it into a priority queue. We will accomplish this with upward heapify and downward heapify. The upward heapify sort the array from the front. It will compare the current node to the parents, and if it's less priority than the parent, it will remain the same place. If it's more priority to the parents, then it will swap and check again. In the worst case scenario, upward heapify will let the node go all the way up into the root, which gives us an n times log of n time complexity. But on the average case, we just need an O of n to build the whole array. Downward heapify will start at the end of the array and check if it has any child. The checking system started once it hits some node that have the child. It will check both children and swap with the higher priority child, and then check if the new child has any child that higher than it. After finally the nodes have been set, it will proceed to find the next node that have child. In the worst case scenario, downward heapify only look at the bottom leaf node's root, which will only contains a fewer layers with constant time. This will bring down the time complexity in the worst case scenario to O of n. So, it is better to use downward heapify to sort an unsorted array into a priority queue. And that's about it. Hope you have learned something about the priority queue, and I guess I will see you next time. Peace.